All right, good morning, Core 3. Sorry I cannot be with you this morning. I have to take one of my children to an appointment. So I just wanted to go through with you what we're going to do today. As noted in the update, you're going to follow along in this video as you work through some notes pages and work through the Lesson 8 Nearpod. I don't want you guys to get farther behind, so I created this instructional video to help you as you work along as if I was actually there in class doing the same. So first thing you need to do is open this deck of cards document. It's going to go into your ISN on page 14, and then this conditional probability slide is going to also go into your notebook on page 15. So if you open up the deck of cards, let me show you what that looks like and talk to you about it just quickly. Looking at this deck of cards, it is a traditional deck of cards, but some people may not be super familiar with how a deck of cards works, so I wanted you to see it visually. We start with an ace, and then we work up through 10, and then there's a jack, queen, and a king, and that's for every suit. So these 4 different things are called the suits. There are hearts, diamonds, clubs, and spades. And then in each of the suits has 13 cards. So it's 13 spades, 13 hearts, 13 diamonds, 13 clubs, 52 cards total in the whole deck. We refer to the hearts and diamonds as the red cards. We refer to the black spades and clubs as the black cards. Face cards are considered those jacks, queens, and kings. Those are the ones over here, the ones that actually have people with faces on them. That's why they're called face cards. So unless otherwise noted, a standard deck of cards will consist of all of these cards. So you're expecting anytime they're talking about a deck of cards that there's these 52 cards in them. You're going to need this reference while you're doing some probability problems today. The other, this is going to go onto page 14 in your notebook. So you're going to click over here so that the slide is outlined in orange. Then you can either right click and click copy, or you can Control C to copy this, and then you're going to paste it into your digital ISN, which is in your drive already. So you're going to open up your digital ISN, you're going to go to page 14, and you're going to paste it in. Then you're going to open up the conditional probability. So opening up this conditional probability, you're going to see all these insert here buttons as we look through this. We're going to fill some of this in together today. Most of it will get filled in together and talk through today, but a lot of it's filled in for you. These red boxes are where you're going to need to fill some things in later. So you're going to click on this slide over here. You're going to right click, click copy. You're going to go to your notebook and paste it in. The next thing that you're going to want to do is, after those are copied and pasted in, feel free to pause it here. The next thing that you're going to do is we're going to open the Nearpod. So I'm going to preview the Nearpod with you while you work through it on your own. It is a self-paced Nearpod, so once you open it up, you will see this screen as the initial screen. Our learning target is to estimate probabilities, including conditional probabilities from two-way tables. So when we move on to the next slide, you're going to have a question to complete. So if you would like a better formatted version of the question, you can click here. Here's a picture of the deck of cards. We've got 2 questions to answer. Noah will select one card at random from a standard deck of cards. Find the probabilities below. Explain or show your reasoning. So pull out a piece of paper, pull out your math notebook where you've been doing your work, and start working on these questions. So you need to A, find the probability the card is a queen. B, find the probability the card is a heart. C, find the probability the card is a queen and a heart. And then for number 2, we have a different situation. Elena pulls out only the hearts from the deck and sets the rest of the cards aside. She shuffles the hearts and draws one card. What is the probability she gets a queen? So pause the video now, take out a piece of paper, compute these probabilities, and then when you're done, you can unpause the video and check your answers with what I have. Feel free to enter your answers as well into the Nearpod slide when you're finished before moving on. All right, so you should have unpaused the video after completing these questions, if you haven't done that yet, please pause it now. I'm going to go through these questions, but I want you to enter your answers into the Nearpod slide if you haven't done so already. You're going to do that while we work through them. So let me pull up my document camera here. We're looking for the probability of getting a queen. So out of a standard deck of cards, there are 52 cards in the deck. So probability of getting a queen. There's a queen of hearts, a queen of spades, a queen of diamonds, a queen of clubs. So there's one queen in each suit, and there are 4 suits. So there are 4 queens in a deck of cards. So 4 out of 52 is the probability that we're looking for. If I take my calculator, and I'm going to divide 4 divided by 52, I get 0.0769, which is going to be 0.08. So an 8% chance of getting a queen. For hearts, there are 52 cards in the deck. Out of those 52 cards, one of the suits is hearts. There are 13 cards in a suit, so 13 out of 52 to get hearts. 13 divided by 52 is 0.25. The probability of getting a queen and a heart, if I'm looking at the deck of cards, there's actually only one queen that is also a heart. So there is one card out of 52 cards. So 1 divided by 52 is 0.019, which rounds up to 0.02. So 2% chance of getting a queen of hearts. Only one queen of hearts in the whole deck. The second problem is a little bit different. She takes all the hearts out of the deck and shuffles them together, and she's picking only from the group of hearts. So if I'm looking only in that group of hearts, I want to know what is the probability that we get a queen. So the way we're going to write that is we're going to say the probability of getting a queen, given that the card is a heart. We've seen this before, but I only showed it to you briefly. So the probability of getting a queen, given that your card is a heart. Well, that means, first of all, the very first thing she did is take only the hearts out of the deck. So we're only looking at 13 cards. Out of those 13 cards, what is the probability of getting a queen? Well, there was one queen, so 1 out of 13. When I divide on my calculator, 1 divided by 13, I get 0.0769, which is 0.08. So the probability of getting a queen, if you're looking at only the hearts, is 1 out of 13, which is 0.08. So this, what we have here, this probability that you're picking a queen after you've already taken the hearts out of the deck and looking at only the hearts, is called a conditional probability. So this is what we're going to be looking at more today and exploring, while we're also looking at independent events. So let's go back for a second. If you haven't already, you need to enter your answers into the Nearpod slide here. So let's keep going. So I was just talking about conditional probability. A conditional probability is the probability of an event happening under the condition that another event occurs. So we are going to talk about this by looking at our notes page. So let's go briefly over to our conditional probability notes page, and let's talk more about what this is and how it looks. And the definition is already written for you in the page, so you don't have to copy it down. All right, so looking at our conditional probability page, here's our definition: the probability of an event happening under the condition that another event occurs. So this word condition is what gets it called to be a conditional probability. So here's the notation. P parentheses A/B is read as the probability of event A under the condition that event B occurs. There are different ways of reading this. This is a very formal way of reading this, A/B, but there are definitely other ways as well to read it out loud. So we're going to go through a couple examples. So here's an example. P of the card is a queen / the card is a heart. This will be read as the probability that the card is a queen under the condition that the card is a heart has occurred. Or you can read it this way. This is the one I prefer. The probability that the card is a queen, given that the card is a heart. In this situation, Elena made sure the card would be a heart by removing the other suits and drawing only from those cards. So what is the probability of picking a queen given that you have hearts? So we talked about this before. This second piece here, the card is a heart, becomes our denominator, and there are 13 hearts in a deck of cards. And out of those 13, this becomes our numerator over here, the number of queens. So there's one queen out of 13, so it's a 1 out of 13 chance, which is 0.08 as a decimal. So think of this notation with this slash. Now this slash, this vertical slash, can be found on your keyboard above the enter button. Like right above that, there's a backslash button and a vertical slash button. Just hold the shift and hit that button to get the vertical slash. So think of this as setting up your fraction. The first thing here you see here, the queen, is what's going to be in your numerator, and then what you see here is what's going to be in your denominator. So you're taking whatever your normal sample space is, you're dwindling it down to just the hearts, and then you're looking in just those hearts for how many there are that are queens. We're going to do a couple more examples together. How would you use the notation to write the probability of rolling a 6 on a standard number cube under the condition that the number rolled is an even number? So to use the notation, we always start with the P. The P stands for probability. Then we use our parentheses. Probability of rolling a 6 on a standard number cube under the condition that the number rolled is an even number. So I'm going to go just in the order that I see it. The first part is rolling a 6. So I'm going to say rolling a 6 under the condition that, so I'm going to use that slash, that vertical slash, or given that the number rolled is an even number. So I'm going to say even. The probability of rolling a 6 given that it's an even number. Okay? So what does probability of even slash number is greater than 3 mean in words? Let's write this out. Well, the P stands for probability, so we're going to say the probability of rolling an even number given that you have rolled a number greater than 3. So first you would look in the group of rolls that you have that are greater than 3. Then you're going to look in that group for the ones that are an even number. So let's do this other example here at the bottom. Example, probability, the card is a 7 given that the card is red. So if we look in a deck, the first thing we're looking for is just the red card. So half of the cards are red. So there's 52 cards total in a deck. Out of those 52, 26 of them are red. So we know our denominator is going to be 26. We're looking for the cards that are a 7. So of the red cards, there's a red 7 of diamonds and a red 7 of hearts. So there's 2 red 7s out of these 26 cards. So 2 out of 26, which when I divide that out becomes 0.08%. So the probability of getting a 7, given that the card is a red card, is 2 out of 26, or 8%, 0.08 as a decimal. Okay, we're going to leave this bottom part for later. We'll come back and fill that in later towards the end of our lesson. But now we're going to continue on in our Nearpod. Okay, so our first practice example here, or situation, is under one condition. Kieran notices that the probabilities from the warm-up can be arranged into at least 2 equations. The probability of queen and a heart is equal to the probability of the queen given that the card is a heart, times the probability that the card is a heart. Since 1 out of 52 is equal to 1 out of 13 times 13 out of 52. Those are the numbers that we had from our schema. You also notice that if you look at the probability of queen and heart, which is 1 out of 52, it's equal to the probability of the card being a heart, given that it's a queen, times the probability of just being a queen, which is 1 out of 52 is equal to 1 out of 4, which was our 4 out of 52. Nope, sorry, that was our 13 out of 52, times 4 out of 52. So if we take the heart-given queen and we multiply it times the probability of getting a queen, we get the probability of a queen and a heart. Kieran wonders if it's always true that P of A and B is equal to the probability of A given B times the probability of B for events A and B, whatever they happen to be. He wants to check additional examples from drawing a card from a deck. So we're going to try these examples at the bottom, and we're going to try to complete them and see if that same thing holds true. We see if when we do the probability of A and B, if it's actually equal to the probability of A given B times the probability of B. So we're going to try it out with these two examples. So I'll read the examples to you and then pause the video and do the workout, and then you can check back to see how you did. In the event A is the card is black and event B is the card is king, does the equation hold? Explain or show your reasoning. In the event A is the card is a face card, in the event B that the card is a spade, does the equation hold? Explain or show your reasoning. So you're going to work on these two, trying to come up with the probabilities that fit this equation and see if it actually works out. Does this side end up equaling this side? Pause, do your work, and then check back.
All right, so looking at the first one, we're trying to figure out if this equation holds true. So our event A was that it's a black card. Our event B was that it's a king. So we're looking to see if the probability of getting a black and king at the same time is equal to the probability of getting a black card given the fact that you've already pulled a king times the probability of a king in general. So looking at these probabilities, I'm going to calculate each of them individually, and we're going to see if this side equals this side. So the probability of being a black card that is also a king. There's a king of spades and a king of clubs. So there are two cards, a card that is a spade that's a king and a card that is a club that's a king. So there's two kings that are black out of the whole deck, which is 52 cards. So I want to see if 2 out of 52 is equal to these two probabilities multiplied. So let's calculate them both out. What's the probability that the card is black, given that it is a king? Well, there are 4 kings in the deck, so out of those 4 cards, 2 of them are black, 2 of them are red. So 2 out of 4 for the probability of it being a black card, given that it's already a king. And I want to see if I multiply that times the probability of having a king in general. Well, there are 4 kings in the deck, and there are 52 cards in the deck, so 4 out of 52. So I want to see if these two things multiply to equal this one. So I can reduce them to fractions, reduce the fractions, or I can change them into decimals. Either way, I can check it out. So if this one, if I reduce, I can divide both by 2, and I get 1 out of 26. Over here, this becomes 1/2, and this becomes divide by 4, I get 1 out of 13. So looking here, I can multiply these. The numerators multiply, and then the denominators multiply. 1 out of 26 equals 1 times 1, which is 1. 2 times 13 is 26. So in fact, they are equal. If I wanted to do them in the calculator and use the calculator to do the decimal, 2 out of 52 is 0.038, which is 0.04. And on this side, it's 0.5 times 4 out of 52, which 4 out of 52 is 0.08. I'll change this to an x because it's confusing. 0.52, so 0.5 times 0.8 is 0.4. 0.08 times 0.5 is 0.04. So 0.04 equals 0.04. So you could do it using the fractions or using the decimals, whichever you're more comfortable with, but it works out. So this equation that he came up with so far is working. Let's try it with the other example. All right, so the second example, we're looking at A being a face card and B being a spade. So we want to do the same thing. We want to say, is the probability of being both a face and a spade equal to the probability of being a face card given you're a spade times the probability of being a spade? My guess is it works, but let's just check it to make sure. It'll help us practice anyway. So the number of face cards we have that are also spades. There are 12 face cards in the whole deck, but only 3 of them are spades. So 3 out of the whole deck are faces and spades. We have a jack, a queen, and a king of spades. So 3 out of 52 are a face and a spade. From looking at this side, I want the probability of finding a face given that I already took out only the spades. So there are only 13 spades, and in those 13, there's a jack, a queen, and a king. So there's only 3 out of the 13 that are spades that are faces. And then the probability of being a spade in general is 13 cards out of the 52 cards, because there's 13 in a suit. So each suit has 13. So are these, when I multiply these two, are they equal to 3 out of 52? Let's do this one using the decimal. So 3 out of 52, 3 divided by 52 is 0.057, which is 0.06. 3 out of 13 is 0.23. And I want to multiply that times 13 out of 52, which is 0.25. So when I do 0.23 times 0.25, 0.23 times 0.25 on my calculator, I get 0.0575, which is 0.06. So this one, in fact, works out as well. Okay, so this formula that he came up with actually works. So let's actually fill that into our conditional probability paper, the notes page that we were working on before. That goes at the bottom.
So opening up your conditional probability notes page, let's fill that in down here. In this, P of A and B is going to be equal to P of A given B times, use a star for that, P of B. So the probability of A given B multiplied by the probability of B is a way to figure out the probability of both at the same time. So having this rule will help us if we don't have a table and we can't calculate them individually. Maybe we're given some information, kind of like the addition rule. It's another formula for us to use that will help us calculate something that we're missing. Okay? Let's continue on with our Nearpod. All right, moving on in the Nearpod, the next slide says a box of 8 crayons, 3 red, 2 blue, 1 black, 1 green, I lost the question, and 1 yellow. Remove 1 crayon from the box at random and set it apart, then remove a second crayon from the box. Use Curon's equation to find the probability that the second crayon is blue and the first crayon is blue. Explain or show your reasoning. So using that formula, which is here in case you didn't want to go back to look for it, using that formula, show me how you can use these two probabilities and multiply them to find this one. So A is the event that the second crayon is blue. B is the event that the first crayon is blue. You're showing out your calculations on how you can use that formula to find this probability. So go ahead and do that and enter it here. Feel free to use a text box or to write it. Go ahead and pause the video to do that. So the probability that we want to find is the probability that the second one is blue, given that the probability, the second one is blue and that the first one was blue. So both of the times we drew out of the bag, we got blue crayons. So we need to calculate the probability that the second one is blue, given that the first one was blue, and multiply it times the probability of the first one being blue in general. So in this bag of 8 crayons, we have 2 blue ones, right? So the first easiest one to calculate is going to be this first probability that the first one is blue. Okay, so if I want to calculate the probability the first one is blue, that's going to be 2 crayons out of 8 crayons total. So it's 2 out of 8. Okay, actually, let me do it this way. So that is going to get multiplied by the probability that the second one is blue given that the first one is blue. So if the first one is blue and I take it out, I now only have 7 crayons. And of those 7 crayons, only one of them is blue. So this conditional probability is affected by the first one being blue. When I took the first crayon out, I reduced the denominator down to 7. And because the first one was blue, it reduces the numerator down to 1. So that probability is 1 out of 7. So when I go ahead and multiply those together, I'm going to get 2 out of 56, which if I divide that in my calculator, I get 0.035, which rounds up to 0.04. So our probability of the second one being blue and the first one being blue is a 0.04 probability, or 4%. Now, one thing I wanted to show you quickly is why this formula is really helpful. If I wanted to actually calculate out this probability of both of them being blue, I would have to list out everything in my sample space in order to figure out how many total options there are, total outcomes there are, and then how many of them are blue and blue. So in order for me to do that, my sample space, I'm going to show you quickly, would look like this. Let's start it for you. So say I pick a red and then I pick a yellow, or I could pick a red and another red, or I could pick a red and a blue, or I could pick a red and a green, or I could pick a red and the other red, or a red and the other blue. I have to list out all of the different outcomes that are possible. So there end up being, I believe, um, a bunch of different, just for red being the first one. Then I have to think about what happens if the first crayon that I choose is a yellow one. I could pick yellow in a blue, or yellow in the other blue, or yellow in a red, or yellow in the other red, or yellow in the other red, or yellow in a green, and the list goes on and on and on and on. So I would end up with 56 different options that I would be listing out in my sample space, and then I'd have to go back through them and determine how many times did I get blue for both of them. So rather than listing out your sample space and it creating this really, really long list and a cumbersome way of you having to calculate the probability, this formula gives us the ability to calculate it quicker. We can calculate this conditional probability, we can calculate this simple probability, and then we can multiply them together to get our total probability of both things happening at the same time. So when I don't have a two-way table and I just have to think about it in a situational example, I would love to use this formula. It's much easier than listing out everything in my sample space, looking at all the possible outcomes, and then determining of those possible outcomes, how many of them are the one I'm looking for out of the total possible. And if I don't even get all of the possible ones written out, then I have my denominator wrong to begin with. So this is one way that this formula will help save a lot of time and help get you more of an accurate answer as well. So let's keep going. How is the probability of choosing the second crayon dependent on the first crayon? I want you to enter your answer here. Think about how pulling the second crayon depends on what you pulled out for the first crayon, and write a quick sentence about your understanding of that question. So go ahead and pause the video, submit that answer, and then keep moving.
All right, so next, I'm going to have you guys do some of these practice problems here. Coin and cube. A coin is flipped, then a standard number cube is rolled. So that's like a die. You're flipping a coin, you're rolling a die. Let A represent the event that the coin lands showing heads, and B represent the standard number cube lands showing a 4. So you're going to calculate these different probabilities, answer these questions. Should be labeled 1, 2, 3, 4, but it's 1, 2, 1, 1 for some reason. So 1, are the events A and B independent or dependent? Explain your reasoning. Use your definitions to help you define that. 2, find the probabilities, A, B, C, D. 3, describe the meaning of the events not A and not B in this situation, then find their probabilities. And 4, are any of the probabilities the same? Is there a relationship between those situations? Explain your reasoning. So pause the video, pull out your piece of paper that you were working on or your notebook you were working in earlier, and calculate these probabilities, answer these questions. When you're done, unpause the video and continue on.
All right, so you have just finished answering these questions about the coin and cube, and you're now going to check your answers. So here are the answers to the questions. Check your work. I'm going to talk through questions 3 and 4. Hopefully you've gotten and understand the answers for 1 and 2. 1, they were independent because since the way the coin lands does not influence the number cube, the way the number cube will land and vice versa. They're completely independent events. Flipping a coin will land on heads or tails. Rolling the number cube will be 1, 2, 3, 4, 5, or 6. They do not have any effect on each other. They don't influence each other. They're completely independent. All right, and then hopefully your number 2, you can check. Okay. So event A was flipping and landing on heads. Event B was rolling a 4. So I'm going to go through what 3 means, because question 3 was not A and not B. And then I'll go through how to calculate those probabilities, and then I'll talk quickly through number 4. I'll turn on my document camera for that.
So since A was flipping a heads and B was rolling a 4, not A would be the opposite, or basically not getting heads, it would be getting tails. And rolling a 4, not B, would be not rolling a 4, so basically rolling everything other than a 4, a 1, 2, 3, 5, or a 6. Okay, so in this example, we were asked to calculate what was the probability of A not B and B not A. So the probability of A given not B and the probability of B given not A. So A given not B would be the probability of A, which is heads, given the fact that we didn't roll a 4. So we rolled a 1, 2, 3, 5, or 6. Okay, so I could have rolled any of these numbers, but getting the probability that I roll a heads is still 1 out of 2 because these rolls don't affect that probability. It's going to be 1 out of 2 whether if I roll a 1, a 2, a 3, a 5, a 6, doesn't matter, or even if I roll a 4. The probability of getting a heads on a coin is going to be actually 1 out of 2 no matter what. So this probability is 1/2. Okay, the probability of rolling of B, which is rolling a 4, given that I didn't get heads, I got tails. Again, I could get tails on the coin first, and that won't affect what I roll. This still has a 1 out of 6 chance that I'm going to roll a 4. So hopefully you'll notice this 1/2 was a probability that we got before. The probability of getting heads, or probability of A, was 1/2. Also, the probability of heads, given the fact that we rolled a 4, was equal to 1/2. And then the probability of rolling a 4 was equal to 1/6, and the probability of a 4, given that I rolled, or that I flipped and got a heads, was 1/6. So you'll notice that these 3 probabilities are the same, and these 3 probabilities are the same. So that tells me that the probability of A happening is equal to the probability of A happening given B happens, which is equal to the probability of A happening given not B happens. All 3 of those are the same. So whether B happens first or not B happens first, the opposite of B happens first, the probability of A didn't change. They were the same. The same thing happened when I'm looking at B. The probability of B was the same as the probability of B given A, which was the same as the probability of B given not A. So all of these probabilities were the same. So whether A happened or A didn't happen, none of that affected the probability of B. So we're going to actually go back into our notes. We're going to need to go back into our independent and dependent events notes to sum up what we just talked about here.
All right, so in our independent and dependent events, we filled in these definitions already. So what we're going to fill in now is we were just talking about these two events, flipping a coin and rolling a die. And we noticed that when I was calculating the probability of getting flipping and getting heads, it was the same as the probability of getting heads, given that I have already looked at rolling a 4. So rolling a 4 had no influence on getting heads, so those were independent events. So when that happens, there is a formula that we can use, or really a formula we can use to check to see if events are independent. If I look for finding the probability of a certain event, so we'll say event A, if it's equal to the probability of um, event A given that event B occurred, then I know the events are independent. So if looking at event B happening first doesn't change the probability of A happening, then these probabilities will be equal. And I mean exactly equal. We had like a half and a half, so they were exactly the same. That makes our events independent. Because B happening first had no effect on A happening, this probability ended up being exactly the same as this probability. So we can fill that in on our notes page, and we're going to use this when we're trying to determine if events are independent in the future. Okay? We can similarly use this when we're looking at dependent events. Now, if events are dependent, when I look at B happening first, the probability of A happening is going to be different than if A happened alone. So when I look down here at our dependent events, we're going to fill in a very similar idea, except in this case, the probability of A is not going to be equal to the probability of A given B happening. And the not equal to sign, we're going to have to use a little shape here. We're going to go up to the Shapes tab, click on this. We're going to go down to Equations, and we're going to choose this not equal to. I'm going to slide this in between here. If you want, you can even change the fill color to be red so it matches the wording. Okay, but when the probability of getting tails is not equal to the probability of getting tails given something else already happened, then those events would be dependent. So think about it maybe in the situation of the crayons. If the probability of getting a blue was 2 out of 8, but the probability of getting a blue, given that you already pulled a yellow out, ends up being 2 out of 7, those are not the same probability. So those probabilities are not equal, and that makes those dependent events. Probability of pulling a yellow out affected the probability of pulling a blue out next. Okay, so let's look at these two quick examples on the next page. So the same kind of situation. A bag contains 3 green blocks and 2 blue blocks. You're going to take 2 blocks out of the bag. So first, before anything is taken out, looking in this bag of 5 blocks, the probability of pulling a blue one is 2 out of 5 because there's 2 blue out of the 5. I lost my text box here. Here we go. 2 out of 5. And the probability of pulling a green is 3 out of 5. But we're going to look at 2 different situations and how they differ. Experiment 1, take a block out, write down the color, return the block back to the bag, and then choose a second block. Let event A be the second block is green, and event B be the first block is blue. So we want to know what is the probability of getting a green after you already pulled a blue one. So we pull a blue one out, put it back into the bag when we're done. It says return it to the bag. There's still 5 in the bag, still 3 green ones, still 2 blue ones. The probability of getting a green at that point is still 3 out of 5. We put the block back in the bag, so it didn't change. So notice this probability is the same as getting a green in general. Nothing changed. These 2 events are independent. So getting a green block the second time and getting a blue block the first time are independent events. Since the first block is replaced, it doesn't matter what block you picked out first the first time when you pick out a second block. The probability of getting a green on the second draw didn't change, since the probability of getting a green overall is the same as the probability of getting a green given that the first time you picked a blue. Okay. When I change the experiment now to this experiment 2, take a block out, hold on to it, and then take another block out, what's happening is I take a block out. It says the first block is blue. I'm going to pull a blue block out. I'm going to be left with only 4 blocks in there. So out of those 4 blocks, I have 2 blue and 2 green. So the probability of getting a green now is 2 out of 4. Oh, I'm sorry, 3. I said that wrong. I took a blue one out. I have 1 blue and 3 green. So the probability of getting a green is 3 out of 4. So I'm looking at a 3 out of 4 probability of getting a green after I've taken a blue one out. Now that probability is different. 3 out of 4 is not the same as 3 out of 5. So this situation where I'm holding on to the block and not putting it back is a dependent event. Whatever block I take out first, because I'm not putting it back, it's now changing what's in the bag. It's changing what the mixture is and now changing the probability of picking out a different block the second time. So when those probabilities are not equal, we end up with dependent events. Okay, so hopefully that explanation was helpful. It'll get easier as we work on it over time. I want you to jump back into your Nearpod and do that quick last cool down question. It's a 3-part question, and then you're going to work on your lesson 8 practice. And then next time I come back, we will work on lesson 9. We're pretty much moving on. So lesson 9, we'll have a formative, we'll have lesson 10, and then we're on to our summative. So we're wrapping up shortly. We'll be taking our summative the middle of next week. So let me know if you have questions after this event, after this lesson, and be sure to work on your homework so that way I can see if there are certain things you guys are struggling with and pick some questions to go over in class. Don't forget to finish your Nearpod and do the last cool down question, and I will see you guys in class on Thursday. Thanks for hanging in, and hopefully this lesson worked out well today. See you later.